Again, 9 talks, 8 40-minute talks, including discussion, and Larisa Goncharenko will give the last presentation, and she volunteered to give a short 7-minute presentation. And I think we have a very good number of really great talks. So the first talk will be given online, so by Jiarong Zheng from Utah State University. Jiarong couldn't come in person, and she will talk about results from the Javara reanalysis data set, looking into the physics of semi-annual oscillations during stratospheric warmings. Okay, so the next talk is given by Han-Li Lu, and Han-Li will talk about the impacts of Hurricane Helene, so this terrible hurricane that caused all the flooding a couple of years ago in North Carolina in the Appalachian region.
Thank you. Okay, so we want to take this as a case study, looking at the gravity waves associated with this hurricane and its impact in the middle and upper atmosphere. I want to first thank my co-authors, our colleagues from the Utah State group, the R group, and also NRL, Steve Ackerman, and the colleagues at HAO and MIT Haystack. So the reason we pick hurricane gravity waves is one reason is because it's very strong. Usually it has a large signal-to-noise ratio in the upper atmosphere. And the other reason is that the scale of the wave is such that for a global high-resolution model like high-resolution WACM-X, we can resolve it. The other reason for picking Hurricane Helene is the AW mission captures this wave at the right time, and also it's seen in the GNSS TEC measurement. And we did a couple of different comparative analysis here. First, we want to look at the large scale because the large scale wind and temperature, they're very important for wave propagation. So we first want to compare the WACM, high resolution WACM-X with Javara and also the high altitude NavGen. I think this morning John was asking about that. I'm not sure if John's here, so hopefully you'll partly address his question. Both Javara and NavGen, they assimilate data up to about 100 kilometers. Apart from that, we also look at the large scale structures from all Javara, NavGen, and WACM-X. And then the gravity waves, we mainly compare between WACM-X and all. We'll talk more in details, but mainly for this one, we focus on the spectral comparison. And then for the TIDs, GNSS, we directly look at the wave perturbations, compare the model results with GNSS results. And I'm not sure if I mentioned that, but one interesting thing is that the waves seen by all, the dominant waves, has a smaller scale. The wavelength is about 105 kilometers, while GNSS has seen a wave scale of about 300. So we'll also look at that. And so the WACM-X, the run is initiated from the nature run for September 29th nominally, and then we apply the nudging for 3 days. It's from GEOS 5 forecast product and up to 1 hectopascal, and then a day before the event, we switch to a very low, only near surface nudging so that the nudging will not kill or damp the gravity waves too severely. So it's more like a free run for the day that this event is occurring. And then Jawara, Jarrell mentioned in her talk, it's a 2-degree horizontal resolution, and NavGen is a 1-degree horizontal resolution. So first, let's look at the large scale. So these are zonal mean zonal mean temperature in the top panel and zonal mean zonal wind in the lower panel from Jawara, NavGen, and WACAM-X for 27th of September. So in general, they look very similar, and which is good. Maybe the notable differences, there are two I want to point out. One is here in the WACAM-X in the radiative mesopulse region around 100 kilometers, WACAM-X tend to be warmer than the two other models. And the other difference is that if we look at the equatorial MLT region, we see that in NavGen, it doesn't show this very strong westward face of the SAO, MSAO. And while in Jawara and WACAM-X, they do show that. And this is the image, the radiance on the left captured, right at the time when Helene made the landfall at the Panhandle, and you can clearly see this concentric waves. And this is temperature. This is radiance, and this is temperature for that satellite track. And you can see this wave signal here in the northern tip of the satellite track. And the main structure you can see here is that it shows a peak warming or warm anomaly in the equatorial region, and then lower temperature on the two sides. And if we look at the temperature from the 3 model results at that time, we see, and this is the satellite track, we see very similar structures. They all capture a very similar structure with the equatorial peak or warm high temperature at the equator, and then cooler at higher latitudes. And the other thing is, if we just compare these 3 model results, they actually give a very similar, tell you a very similar story about large-scale structures. And for example, at the equator, it's a superposition of wave number 1 to 3, and likely from various tides and probably also Kelvin waves. But in general, they look very similar, even at higher latitude. The main thing is that here in WACAM-X, it looks much redder, again, showing the kind of the warm anomaly in the model. And these are 3 comparisons, this from all, and all the tracks on September 27th, and this is from Jawara and NavGen. I didn't put WACAM-X here because we only have 3 hourly output for WACAM-X due to the large data volume. So here are all hourly results, or nearly hourly results. But again, they look quite similar, especially between all and NavGen. The structure looks rather similar. And then this is along the temperature profile along the track. It's a cross-track averaged, and this is solid line is all, and then the dotted line is Jawara, dashed is the NavGen, and dash dot is WACAM-X. So the general structure looks similar, again with WACAM-X having this about 10K warm bias. And in the southern hemisphere, you can see that the all Jawara and NavGen have very good agreement, except some warm anomaly in the place, maybe capturing some part of the planetary wave. And then in the northern hemisphere, Jawara appears to be cooler, and while NavGen appear to be warmer than all. So now if we look at the waves, the perturbations, these are all from WACAM-X. The vertical wind in the stratosphere, this is at near 87 kilometers, and this is in the 250 kilometers. So you can see that they all show the kind of concentric ring, structure, and even in the in this altitude there are a lot of other signals, but still you can see this this wave structure centered around where the hurricane is, and it's especially clear. In the thermosphere. A lot of the other signals are gone or filtered or damped. But one thing we note is that even though the general structure of the wave looks similar from the model compared with all measurement, the wavelength is much larger. The wavelength here resolved by WACMX is between 200 and 300 kilometers, while what's the most prominent feature in all is 100 kilometers. So this is most likely is due to the limited resolution. The model cannot resolve the most prominent features. So instead, that's why we switched to, for this comparison, we want to look more at the wave spectrum rather than just that specific wave component. And so look at the spectrum. This is the vertical, the black line is the all horizontal spectrum, and this is the equivalent zonal wavelength, zonal wave number, and we take the whole track so that it has a very broad spatial range, spectral range. The first thing we notice is that in all, it does reproduce this minus 5/3 law, power law distribution, all the way down to about zonal wave number 1,000, which is about 40 kilometers. So just like the lower atmosphere, it hosts this power spectrum distribution very well. And the red is from the WACMX temperature directly from that level, from the simulation. And it overlaps with the observed spectrum up to about 140 zonal wave number 140, which corresponds to about 250 kilometers, and 285 kilometers. So beyond that, it drops. And then this one is OH layer averaged, and so you can see that does kind of damped out or not smoothed out the waves so that the power is lower. And so this is just quickly show the TID comparison. The TID in general looks very good. The wavelength is very comparable, though the magnitude in general is underestimation. And it depends on which direction you look. It may be underestimated by 50% to maybe 30%, 30 to 80%. The reason we want to look at this is because we want to use this to calibrate our estimation of the global energy flux, because this one is showing in the original simulation where at the 100 kilometers we show this total energy flux from 50 to 150 gigawatts. But if we're systematically underestimating the waves, gravity wave amplitude, maybe it does play a maybe it's much more larger than what the model is currently telling us. So it may play a much more important role than we thought in the thermosphere energetics, the gravity waves. So I think I will stop here and leave the summary and take questions if you have any. Thank you.
Thank you, Han Li. Okay, so Fabrizio first. Sassi.
The figure on for the drop of the spectrum, and the fact, that the red line is well below the black line. Is it because dissipation of those scales in the model?
Yes, there are two parts. Beyond this part, it's most likely due to the various numerical diffusion and truncation.
Right.
And this part, if we trust the OH average, layer average, This part is likely due to maybe the underestimation of the source strength or the dissipation when it propagate, numerical dissipation during the propagation.
Ali,
Yes.
always you give a nice talk. So if you go back to the temperature passes, and
Here?
no, the other one, this one. So I can see the model and how they match very well, I guess. But I'm asking you for the how was the cloud availability during that time? Cloud availability.
Oh, cloud. Oh, I see.
Because the cloud also caused that kind of structure.
That's right. Oh, you mean the red structure? You think
Yeah.
it's cloud?
Yeah.
No, I think this is already corrected. I think someone else from the all group can speak better. But there are actually, I looked at quite closely. There are, I think, during the day, during that day, there are maybe 2 or 3 orbits where the cloud contamination is very severe. So that's why if you include all the observations within that day, you actually get a, where's this? Oh, here. You actually get quite a large, small scale power from those observations. So those you can tell that there are cloud contamination, especially on smaller scale. They like appear as speckles. But when we do the spectral analysis, for example, we take that out, and then you can see, this is free from those cloud contamination. So I would say on that day, it's not very severe, except maybe on 2 or 3 orbits from the cloud.
So, Hanli, over here.
There.
This is where I think all might have the most problems, though, with clouds, because they use the Q-branch line to get rid of their clouds. Q-branch line typically will reflect at 10, 11, 12 kilometers, and the hurricane clouds, of course, are much higher. And so you might expect the Q-branch technique that they're using, which is very successful elsewhere, would have the most problems over a hurricane.
Yes.
Now, the more people can respond to that. I'm sure they've looked at that a little bit, but
Yeah.
this is probably a more problematic situation.
Yes,
than normal.
actually, that's why here when we compare the temperature and also the spectrum, we exclude the tracks like this. Here, this may not be directly related to the hurricane itself, but you can see if for whatever reason along this track you do see this kind of speckles I was talking about. But out of the 15 orbits on that day, only 3 kind of have such
I'm
bad.
just saying it's difficult with the Q-branch technique on the temperatures here. That's all.
Yeah, I agree, but I think the temperature doesn't use the Q band, right? The Q band.
We do use the Q line to correct P12, P14 for lower clouds. But for higher clouds, as you said, you're right, we have trouble. Yeah, but for the low clouds, we have no problem. Yeah, if you look at the Q line, a lot of time when we show the concentric waves, you see some cloud patches there that we couldn't do much.
But the problem is the hurricane clouds also, especially when you get close to the center, look like concentric waves sometimes. So you have to be very careful.
Okay, one final question from Li Ying.
Hi, Han Li. You showed power, the gravity wave power and the Zhu heating solar irradiance power.
This one?
Not this one. I think
Oh,
it's later.
I see. Yeah,
it's
yeah.
later.
Okay, right.
Yes. So it says gravity wave power is 100.
So yeah, this is the current estimation according to all the resolved waves in the model. So it's from 50 to 150
Yeah, so
gigawatts.
So it's comparable with Zhu heating power.
It's comparable with the Joule power the daily average Joule power.
Yeah,
but
on
what I
daily.
was saying is that if we if we believe, the calibration work we're doing here, actually this power may be 4 times larger. So it could be from 200 to 600 gigawatts. So on average, you may get much larger power, gravity wave power than what we currently believe from this estimate.
So compare with the gravity wave power with Joule heating power. Actually, is this gravity wave power is larger than Joule heating power on daily average?
Yeah, at least this is at one altitude, 100 kilometers. So this is the total power that got into the thermosphere.
Right.
So at a specific altitude, maybe it's not dumped at a specific altitude. It's distributed over a certain altitude range. But the total, if we count the total, it's comparable or maybe even larger.
Yeah, this is from energy point of view. That thing, this is like, what implication is this? I'm just, this is
Good question.
You need to think about that.
Something
yes.
to explore maybe in the future.
Yes,
Yeah,
yes.
that's right.
This is quite significant. Okay, thank you.
Okay, thank you, Han Li. So Benedict is still working on uploading his talk. So Mambarat, are you ready to step in? Okay, so then we will switch the order of the next 2 talks. So, Mambarat Dudley from NRL will talk about MSIS and HWM results of the new versions that are in the making and what they do to the ionosphere.
Hello everyone, I am Manbra Dali from NRL, and I'm going to present on the current status of horizontal wind model with the non-migrating tides. And so the basic goal of this project is to include or incorporate non-migrating diurnal and semi-diurnal tides in HWM, and those tides are based on CTMT model from Dr. Jens Oberheid, and we are calling this new model as HWM 2.5, or you can say HWM 25. Because we started it in 2025. All right, first is the background and motivation. So we all know that HWM is an extensively utilized global characterization of neutral winds. And HWM is based on past several decades of wind measurements, and it serves as a kind of benchmark for assessing new measurements from satellite ground-based stations as well as models. But it was lacking non-migrating tides. And the figure that's shown on the right here, that serves as a big motivation for updating HWM and including non-migrating tides. So this figure shows zonal wind as a function of longitude. Here we have meridional wind as a function of longitude, and each row shows winds at different altitude. And these altitudes are between, for example, 90 to 95 and going up to 100 to 105 kilometer. Black curve is from are the mighty measurements, red are the tidy measurements, and green is HWM 14. If you look at mighty and tidy, they show pretty interesting longitudinal oscillations in zonal wind and meridional winds. Since this figure is at a fixed latitude and fixed local solar time, these oscillations, they are due to presence of non-migrating tides and stationary planetary wave in the observations. But HWM14 do not have these non-migrating tides incorporated in it. That's why it's totally flat. And that's why we wanted to update HWM to incorporate non-migrating tides so that we start getting similar oscillations in the winds. So approach that we use to update HWM is that we are using a CTMT, non-migrating tide. CTMT is a climatological tidal model of the thermosphere by Dr. Jens Oberheid, and it has 9 non-migrating tides. 4 are diurnal, 5 are semi-diurnal, and CTMT tides, they are based on observational climatology of tides that are based on 20 years of SABRE and tidy data. And these tidal fits, they start at the ground and goes up to 400 kilometers. But in HWM, fitting of the tides, we are using tides only above 70 kilometers going up to 400 kilometers because below 70 kilometers, non-migrating tides are kind of negligible. And for fitting these tides from CTMT in HWM, we are using vector spherical harmonics in latitude, longitude, universal time, and seasonal harmonic going up to terannual oscillation, and then vertical cubic B splines for vertical fitting. So this is what the mathematical formulation of that we are using in HWM for fitting non-migrant tide looks like. Beta H here represent the vertical basis, and UH is the combination or coupled term between vector spherical harmonic and seasonal harmonic. I wouldn't go in detail here because it's going to take a lot of time. I can directly jump to the results. So here's an example result showing D3 tide from CTMT and HWM25. So on the left we have zonal wind amplitude, right? We have zonal wind phases from CTMT and HWM as a function of altitude and latitude. So each column is for a different day of year, so basically seasonality. And here we have phases in the same format as amplitude. And if we compare CTMT D3 with HWM 2.5, you can see they're pretty identical to each other. That means the formulation we have used in fitting D3 in HWM 2.5, that's pretty solid, and it can reproduce what is in CTMT model. However, there are some differences in the phases between CTMT and HWM above 60-degree latitude, and that's because the amplitude at these latitudes, amplitude of D3 at these latitudes are zero, and the phase doesn't have any significance there. That's why they're different. We performed such testing with all the CTMT, all the 9 CTMT tides in HWM, and we got a similar results, pretty robust fitting in HWM 2.5. And then we compared HWM 2.5 results with the ICON MIDI measurements. So here in the figure, we have zonal wind as a function of longitude for 3 different seasons: winter, equinox, and summer. And here, each row is for a different latitude bin. So all the latitudes that are covered by ICON MIDI measurements. So if you look at black curve are the MIDI measurements as a function of longitude at different latitude, and you can see these oscillations. And these oscillations are at a kind of fixed local solar time latitude. That means they are due to the non-migrating tides and stationary planetary wave. And if you compare black with blue as HWM14, HWM14 is pretty flat because there are no non-migrating tides or stationary planetary waves. But if you look at HWM 2.5 or 25, you can see it's following what is in MIDI. That means we are reproducing what is present in MIDI. So if you compare HWM14 and 25, like a red and blue curve, you can see that HWM25 has basically improved a lot over HWM14, and this is a comparison with the observed data set. And then we looked at the altitude-longitude comparison with MIDI. So here we have zonal winds at noon around equator. Here we have meridional winds at noon around equator. Left column is for MIDI, middle column is for HWM14, and right column is for HWM 2.5. And these winds are shown as a function of altitude and longitude for 4 different seasons. What we see in MIDI data is there's a prominent wave force structure that extends from MLT region going all the way up to the thermosphere. If you look at HWM14, it's missing all these kind of wave 4, wave 3, or wave features. But HWM25 or 2.5 shows similar wave structure as present in MIDI. So if you compare 2.5 with the 14, it shows a remarkable improvement over HWM14. That's one thing. And then we did some fun experiments because now we have formulated non-migrating tides in HWM. Parallelly, we were also working on updating non-migrating tides in MSIS. So we have non-migrating tides in HWM and MSIS. We can turn them on, turn them off, and turn them on in one, turn them off in other one, and vice versa. So we can we planned some fun experiments with it. For example, using turning on the tides in the models, we can quantify the role of non-migrating tides on the ionosphere. And then we can look at what, excuse me, what is more important, non-migrating tides in neutral winds or non-migrating tides in neutral temperature or composition, or both. So these are kind of experiments we did, and this is what the results look like. First is quantifying the role of non-migrating tides on the ionosphere. That's pretty simple experiment, but pretty robust results. Shown here is the NRL SEMI output that's run with the first column is without non-migrating tides in HWM and AMSIS. Shown here is electron density, TEC, NMF2, and HMF2. The second column is NRL SEMI ionosphere with non-migrating tides. So first is without non-migrating tides in thermosphere, second is with non-migrating tides in the thermosphere, and third is percentage change. Now, these panels, they are at a fixed local solar time, and we use fixed local solar time because we didn't want any day-night asymmetry in electron density. We really wanted a clean picture. And if you look at the percentage change, it clearly shows the role of upward propagating non-migrating tides on electron density, TEC, NMF2, and HMF2. And if you look at these percentage change panels, you can clearly see a distinct wave pattern present here, almost everywhere. And if you look at the magnitude of these changes, that's kind of plus minus 30%. So non-migrating tides are kind of changing the electron density by plus minus 30%. And if you look at HMF2 is changing by plus minus 40%. So that's the role of non-migrating tides playing in the ionosphere. And second, we looked at where the tides are important. Are they what's the role of non-migrating tides in neutral winds versus the neutral winds, neutral temperature and composition, sorry. And here what the results look like. So we have case one where we have, and these panels, they show percentage change in the same format we saw in this figure. So case one, we have a NRL SEMI run with non-migrating tides in both winds and temperature composition. Second is non-migrating tides only in the winds. And third is non-migrating tides only in the temperature and composition. So if you compare case one with case two, they look pretty similar. But case one and case three, that show big differences. Now case one, case two, they're pretty similar. That suggests that the non-migrating tides in neutral winds, they are playing major role, or they're the major contributors of the longitudinal oscillations we are seeing in the ionosphere. And if you compare case one and case three, we can see that the neutral temperature and composition, or the non-migrating tides in neutral temperature and composition, they're playing some role, but those roles are secondary. The major contributors are the non-migrating tides in the winds that are creating longitudinal oscillation in the ionosphere. Summary and future work. So in the summary, 9 upward propagating diurnal and semi-diurnal tides has been added to HWM based on CTMT, and they are producing pretty nice longitudinal structures in the winds. And we have compared and validated those oscillations with the icon mighty, time tidy, and UR's windy. Here's data I'm not showing here, tidy and windy due to time constraint. And anticipated release of HWM 2.5 is before AGU. So in future work, we are integrating our high latitude wind model with the HWM. High latitude wind model is in geomagnetic coordinates, and HWM is in geographic coordinates. But at high latitude, winds are more organized in geomagnetic coordinates. So we are using a hybrid approach to merge these two models. And details of this project will be presented tomorrow in the oral science session. We'll stop here, take questions. Thank you.
Thank you, Mambarat. That was very impressive, and looks like I can retire CTMT soon. Okay, so we have time for perhaps 1 or 2 questions.
Hi, Memrat. Yeah, it's so impressive. But what if you compare the non-migrating tides with migrating tides? Like, for example, compare with SW2, DW1, its impact on the wind, how that to compare?
Right, I mean, that can be totally done. Like here, we were updating only non-migrating tides. So we were like, okay, let's just look at the role of non-migrating tides. But role of migrating tide can also be looked the same way because we have options to turn off those tides in MSIS and HWM. Yeah.
So
We can do the similar experiments that are really hard to do in the physics-based models.
okay. So basically, that says, because the non-migrating tides mainly impact the ionosphere through the wind, not the temperature and composition. So that means it is mainly impact the ionosphere through the dynamo. Is that right?
Yes, that's a major thing. But if you look at this panel, you can see that there is some changes. The temperature, non-migratory tides and temperature and composition, they're bringing at high latitudes.
At high latitudes.
At high latitudes.
Okay,
So the
that's-
role of non-migratory tides and composition and temperature may be prominent at high latitudes compared to the equatorial regions, where the oscillations are like longitudinal oscillations are mostly driven by the wind dynamo. Yeah.
Very interesting.
I was
Thank you.
surprised to see this result.
Yes, yeah. Thank you.
Excellent work and really far-reaching implications of this. Thank you. I had a very simple question. Maybe you already did this type of exercise, but have you estimated out of all the non-migrating tides that you included, can you say if there are, like some of them are much more important than others? So this is contribution from all non-migrating tides.
Yes.
So what can you say about importance of particular contributions from particular tides in particular as a function of season?
Right, we would have to check on that, but I can say that DE3 would be the most important because it's the biggest tide out of the 4 or 5 non-migrating tides we have in CTMT. So DE3 may be the biggest contributor, but we definitely have to look. For example, if you look at the composition panel here, DE3 doesn't go up to the poles. It just dies like at amplitude, at maximum around equator, then amplitude kind of goes really low above plus minus 40 degree latitude, right? So above those latitude, other tides may be contributing. So we would really have to do those experiments.
Okay, thank you, Mambarat.
Thank you.
Okay, so now switch back to Benedict Pinheiro, so where we will learn about nonlinearities in gravity waves and dissipation and propagation.
Hard act to follow. Thank you, everybody. My name is Benedict, and I'm going to talk about nonlinearities and convectively generated waves, specifically gravity waves, and the impact of wind variability. So just as the structure of the presentation, we're going to go through a general background. The presentation just preceding us talked about HWM. This one will talk a little bit about it as well. I'm an HWM user, so I appreciated the talk as well. I'll go through a mathematical description, which will all lead to sleep. Then we'll go through the numerical solutions of those, because this is a modeling talk. I'll provide some discussions about things that are mostly linear with some nonlinearities, and then we'll talk about future work. So as I was listening to the previous talk, I saw some HWM sort of discrepancies and maybe some updates to it for AGU 2026, and I was motivated by one of my lab mates, Sophie Phillips, to create this sort of video of the maximum or minimum of the zonal winds that HWM predicts for all lats and lons. So it kind of stays within a range of 110, plus or minus 110. Similar thing was, this is kind of like my sort of lava lamp thing. Similar things were done for the meridional winds. So as you can see, it's not really varying too much. I don't know if this is playing. Yeah, it's not, the variations are within plus or minus 110 meters per second. This is within 90 to 120 kilometers. So that has been known to be sort of underrepresented, and like there's tidal influences, as the last talk talked about. And these HWM models are used by modelers, by people that do observations to derive wave characteristics of observations. So it's relevant that we get these parameters right. So as was discussed, there are previous papers that have discussed how these are underestimated. So there's a motivation to see if you amplify the wind, what effect it will have, and will it be more realistic. It's kind of the main idea behind the talk is how does enhanced wind variability near the turbopause drive linear or nonlinear dynamics and momentum transport. So quickly go over the math. We do modeling, and most of the people that do modeling are trying to solve some form of the Navier-Stokes equations or parameterize it. So we are included in that, and these are the multi-component Navier-Stokes equations, so they are aware of the species and the impact that they have on energy diffusion. The only equations on the left are the sort of talking about the transport of the wave, and the diffusion of the fluxes are on the right. So that talks about momentum diffusion through viscosity, thermal conductivity, heat diffusion, and species diffusion. They're kind of broken down here. I won't spend too much time on this, but this is the what's typically known is that shear viscosity and thermal conductivity affect the wave propagation, especially in the thermosphere. And the newer terms that discuss species diffusion are things that were published recently by myself and Jonathan Snively and Roberto Sabatini. What these equations allow us to do is to obtain the sort of molecular diffusion parameters that affect the wave propagation, especially in the thermosphere, and it allows us to obtain them in a way that is self-consistent. So as long as you know the properties of a molecule, you can calculate the dissipative coefficients. So instead of relying on empirical expressions, you know about 5 or 6 parameters, and you can do it for any planet, any gas, anytime. So these equations are solved with a Jonathan Snively developed a magic model, and it's a forest claw implementation, which basically means it solves the Navier-Stokes equations, and it uses AMR, adaptive mesh refinement, so it'll refine, or it'll focus on the areas where there is a certain tolerance for, let's say, like the velocity needs to be more concentrated on. This allows for the model to solve for things quicker. Some of these gravity wave simulations take forever. I come from acoustics, especially in 1D, so I could get a result in like 2 minutes. This takes 5 days. Oops, going back. And just as an example of the coefficients that are calculated, this is thermal conductivity based off of several people that are known in the field with 2 species atmosphere versus a 3 species atmosphere. So you can see already it's important to get these coefficients correct. For the wind, I took a case of the Meritu winds, which are also combined with HWM. I have a little gray zone because that is where the marriage happened, so beware. And we'll be focusing on 2 cases for this presentation. It'll be very preliminary, sort of fresh results from like a couple minutes ago. And for the source, there is a convective source, which is inspired by the Nolan and Day. And what they have is basically like a super Gaussian, and Gaussian solutions are very common in numerical modeling. So a super Gaussian is meant to reflect the convective storm. And if you have, for example, you have a Gaussian here, if you have sigma sub t, if it's smaller, you have a very convective source, it'll shoot up. So this is added to the energy equation. And you have some diagnostic metrics which are used by everybody. So here I'll just show some results. We have the configuration that I'll be using is there will be like an XY slice, an XZ slice, and a YZ slice. YZ meaning like the meridional direction, XZ meaning the zonal direction, and XY is just a slice through the middle. So we have a source that I discussed earlier, and it plops some energy into your field, and then you get some acoustic waves, you get some gravity waves. This is about at half an hour. The slice at 200 kilometers, according to the case I was trying to replicate, should have been around 180 kilometers. I think later on it'll become that once the acoustics sort of dies down. As you continue, you get these gravity waves and you get some filtering because of the wind profiles. This is of the normal wind profiles, not the amplified ones yet. This is again some XY slices showing you how the concentric rings, which are common for convective storms, and how they sort of evolve as they propagate upward. You can see that there's some diffusion going on. You can see that there's some sort of Doppler shifts. And this is for the future, but this is an instantaneous gravity wave drag and momentum flux. The idea is to collect them at several timestamps and then do a sort of an average of them, and you'll get your wave field. So for the stronger wind versus like a sort of normal wind case, where normal being whatever HWM predicted, when you have a stronger wind, you get, as I said before, you get some filtering, you get a preferential propagation of the wave. That's what the top is, the stronger wind case, and then the amplitude is larger as well. Amplitude is larger because of selective spectral energy spreading towards other dimensions because it's not, because it's being filtered out by the wind. This is a YZ slice, again, a meridional direction as is labeled, and you have this direction looks similar because the winds for this direction were similar. So the zonal ones will look different because they were different. As time advances, you get more sort of dissipative processes occurring at around 100 kilometers. That's where there's a large shear, especially for the stronger wind case. Meridional direction looks similar again. So some final thoughts, there's some evident filtering occurring due to the eastward winds and some selective damping. This requires some more future sort of some diagnostics to actually demonstrate this rather than just show you the wave field itself, which hopefully I can provide on Thursday at my talk. There's a higher wind case that resulted in greater fluid speeds, and future work I can amplify this even more. This is the role of modeling. We can play with the parameters, how fast the convective source was or how strong it was, and we can get braking, we can get maybe secondary winds, who knows. But anyway, thank you.
Thank you, Benedict. Time for questions.
I know I'm a co-author, but I still have a question. So on slide 31, you had what looked like a really cool secondary wave emerging from the one side of the domain.
31.
How long did that take to establish? What was the time on that one?
4 hours.
Oh, okay. So it took a few hours after the initiation.
Yeah.
Okay.
Yeah.
So the timing of the arrivals of the primary wave, is that on the order of like an hour after it started?
Yes. Yeah.
Okay. Cool. Very nice. That's nice that you have a separation in time that you can quantify that in the simulation and see when to expect primary versus secondary.
It would have been labeled. I was out of time, so.
Yeah, I totally understand. Sometimes the cluster is a little bit temperamental. So cool. Thanks.
Okay, thank you, Benedict. So our next speaker is Fabrizio Sassi, who will give us an update on the GEOS MLT development.
Cool. All right, I'm Fabrizio Sassi from NASA Goddard Space Flight Center in Maryland. And I want to give you an update on the development of a new upper atmosphere model, which is the extension of the GEOS model into the lower thermosphere. This is a partnership between two Goddard divisions, the Heliophysics Science Division and the Earth Sciences Division. The team you can see here, listed here, they're all great people, and all the progress that has been made is because we have a great team. So the focus of developing this model is to understand better the ITM, which I tend to define as an interstitial domain that connects space and terrestrial weather. It's like a place where they handshake and two types of physics, the neutral dynamics and the electrodynamics, terrestrial weather and space weather, come together. And that's really the place where you can see these impacts on many practical applications, from radio wave propagation to spacecraft navigation and so on. So in order to do so, we took the GEOS model, which is a very reputable NWP, numerical weather prediction model for the lower atmosphere. It extends to about 80 kilometers, but it ingests observations only up to 60 kilometers. So really, below the stratopause, it's realistic, and above the stratopause, the mesosphere starts to become iffy. So the idea, as the figure in the middle says, that we want to extend this profile to about 210 or 220 kilometers. And the valid domain for ingestion of observations is essentially up to 150 kilometers. So where are we? We got funded through an internal funding system at NASA. And we are in the second year of this project. We have 3 years in total. We have successfully extended the model to 210 kilometers. We are able to parameterize MLT physics, and I will explain what I mean by that. And we are doing now model verification. After that, we will deal with the model MLT data simulation, model validation then, and then the ultimate goal is to do retrospective analysis like a MERA2 on steroids, because we will do retrospective analysis from the ground to the lower thermosphere. So this is the table of where we are, what we have done. You can see the list there. The blue is things that we have completed. The black is the one that we are still working on. So let's go one by one. We have extended the domain to 210 kilometers. These figures show the approximate layer thickness. The red one is the GEOS MLT, and the black one is the GEOS native model. The idea is that the two are exactly the same below 80 kilometers. And the idea is that we do no harm in the GEOS domain. But we have our sandbox in the upper domain where we can add physics and resolution. One problem, I don't need to explain this to this audience, but as we know, a problem of extending models in the upper atmosphere is the variable composition, which changes the equations that we need to solve. Changes the thermodynamic equation, and Hanley demonstrated that the equations in one of his papers, and specifically for the FV dynamical core, and the hypsometric equation, which is essentially the integral of potential temperature in altitude to get the geopotential altitude. These equations are solved in the dynamical core, FV3, and all those changes include the fact that the thermodynamic quantities, kappa, and what do I see here? Mostly kappa, are a function of altitude, and kappa itself is R over Cp. So you can look at the figure on the top right, which is a paper from Eckermann at NRL, and it shows the profiles of these constants, As you go above about 110 kilometers, they are not anymore the whole the homogenized atmosphere, but you started to have a species separation due to their weight, and so the constants have different values. So all of these had to be included in the dynamical core. But also we had to include some components of the physics, which is for thermoconduction. Thermoconduction is very important because it takes heat from the exosphere and it brings it down into the thermosphere. Without thermoconduction, your thermosphere will be cold, will be a refrigerator. We took a standard formula from Bank-Cockart that you see there, and then we added the solution for the diffusion equation that you see there, where lambda is our conductivity. That's fairly straightforward. But then we have to deal also with the molecular viscosity. I know there are analytical formulas for the molecular viscosity, but I decided to take a different path. The relationship between molecular viscosity and thermal viscosity is expressed by the Prandtl number. So once we have calculated the thermal conductivity, and we decided to have this Prandtl number as a tunable parameter, we can calculate a molecular viscosity. This is, I mean, people do differently, calculating explicitly momentum viscosity, and then they adjust the coefficients for their model simulations. We decided to be upfront clear that we are using the Prandtl number as a tunable parameter. And all of this is included in the dynamical core. We don't do this in the physics, we do this in the dynamical core. And then the MLT parameterized the physics differently from my friend Han Li, who is dealing with a model that has interactive physics and chemistry. We do not have interactive physics and chemistry. The only way we can do this is essentially the same way I did Wacom 25 years ago. You take the output from another model and you do a lookup table to calculate the heating rates. Fortunately, I have people who are much smarter than me and younger than me, and one of my postdocs created this machine learning system that is trained on a WACAMX simulation, a 10-year WACAMX simulation, to get the shortwave heating, long-wave cooling, Joule heating, chemical potential, all the things that enter the thermodynamic equation on the right-hand side. And an example is this nice movie where you see the first one is the short wave, you see the diurnal cycle, then the middle one is the long wave, and then on the far right is the Joule heating, which is very variable depending obviously on the solar constants. So this allows us to do MLT physics without having the physics and the chemistry, which actually is going to be what we want to do if we get funded more. Plug. And the remaining thing is the ion drag. Ion drag is also a very simple formula, but again, we need to have the ion velocities because it's the frictional momentum between the ions and the neutrals. And if you don't have the ion velocities, what do you do? And so again, this very smart postdoc of mine decided to use machine learning to train to be trained on the output from WACAMX, from which we get the ion velocities. And then the other constants that or variables that enter these, the ion drag is the conductance and ion densities, which are obtained from IRI. So all of that we are working, actually, I was told that is already in the model. But there are more complications that we have not considered, and they are not part of this project because they are very complicated complications. One is the geometry, because when you start to be in a domain where the altitude above the surface is comparable to the radius of the planet, all your geometric factors are needed to be to account for this factor. And if you do the math, at 50 kilometers, the correction is less than 1%, but at 500 kilometers, the correction of the geometry of the size of these elements can be 4%. These are important aspects for if you want to do spacecraft navigation or a vehicle re-entry, because you need to have all these terms calculated very accurately. The same for the acceleration of gravity, as this is more straightforward. We know that most models use 9.8, which is the value at the surface. But if you account for the elevation above ground, then things start to be a little bit different. This is actually straightforward to implement, but we have not implemented. And then there are the apparent forces, because we are describing the atmosphere in a rotating frame of reference, and so we have to add all those components that are apparent forces. And typically in a model, these are the Coriolis forces, so the longitudinal and meridional Coriolis force. But when you go to a non-hydrostatic formulation, there are many more complicated formulas, many more complicated terms that couple actually the horizontal and vertical momentum. And as you can see here, this term needs to be added to the momentum, the momentum of in the dynamical core. They are, I think they are already included, but we have not tested those, so we don't know how and if it will work. So again, this is not work we are going to do now. I'm just lay the ground for what still needs to be done. And this is so for the future. For data simulation, we want to use many observations, so that, for example, the NavGem HA system used in the old days, and we are starting to do a CEDAR data simulation using a CEDAR. We will see how much we can bite out of this list, because time and people are very, very limited. But as you can see, it's a long list that can include many more observations. So conclusions. The GEOS model has been extended from 80 kilometers to 210 kilometers. Variable composition and thermoconduction molecular viscosity have been added. And we have a nice machine learning system that allows us to solve for the MLT physics. And the next step is validation and verification. Our aspirational goal is that if we continue to be funded, we want to add the relevant chemistry, which will then allow us to do interactive chemistry, and we can then play in the same playground as my friend Han Li in the thermosphere. So from a more of, I don't want to say agency point of view, but the goal, the ultimate goal for NASA is to have a whole atmosphere system. We started from GEOS at the bottom. We added parameterized physics and chemistry, so we get to MLT, which we are finalizing now. Then the idea is to add interactive physics and chemistry, which will be a GEOS high altitude. And then if we can continue to be funded, then we want to have interactive ionosphere, which then will allow us coupling with space weather drivers, and that will be a GEOS whole atmosphere. And that is it. Thank you very much. Ali, my friend. Sometimes.
Question for your funding mechanism. For outside world, geo is geo and helio is helio.
Right.
But it sounds like you were able to, for this project, you were able to kind of have the two work together.
You're pointing to a very difficult problem, because this funding is really siloed in silos between the divisions. But yes, in this case, it was appreciated that both divisions have a common interest. The heliophysics division, because they wanted to do eventually support missions, and so do OSSIs and all these kind of things. And the Earth Science division, because they want to use observations in the mesosphere. They have a very deep field of view, and so in order to do that, they needed to have a model that extends to the lower thermosphere. So there was a common interest, and then we were able to get this funding for now. Oh yeah, no, definitely. This is going to be a community model. It's not going to be something that we hold to our chest. I mean, eventually. Oh no, I mean that. I mean, there are program managers back there, so I'm not going to speak about the funding. But yeah, no, this is internal. It's called ISFM, Internal Science Funding Model. It's just for internal funding scientists.
Fabrizio, very
Oh, there.
very nice progress and with development. Thank you. My question is about verification validation. What MLT radius are you considering? What specifically latitudes and so on, and how many radius do you have?
How many what?
How many radius are you planning to use to verify?
For the interactive chemistry?
No,
I'm sorry. For the
yes.
validation. Well, we needed to use observations that obviously we are not going to ingest. So hopefully we are going to choose a set of observations up to 150 kilometers, and those will be used for the validation. So first the retrospective analysis and then the validation. If I answer the question correctly, if I don't, let's talk afterwards.
Yeah, let's talk during the...
Okay, I'm sorry.
Thank you.
So I have a very short question, perhaps. Can you go back one slide to your hierarchy? So let's assume for a moment funding would not be the issue. So what's the timeline for that?
It's not going to be easy, but it's doable. The interactive physics and chemistry has been done before. Wacom-X has these packages. And this can be done probably in a year or two, and then testing in the second year. And then the coupling with the ionosphere, that is very hard. I've done that at NRL, and it took me 3 years. So that's the timeline.
Okay, thank you, Fabrizio. So the next speaker will be Enrico Ruiz Villalbar, who will talk about constraining neutral wave perturbations from TEC signatures with reduced physical models.
Okay, hello, I'm Kike. I work at the Haystack Observatory, and I'm going to talk about reduced models and how to use reduced models to analyze data. So these are the contents. Let's see. Okay. So as you probably know, if you have system parameters and you want to reproduce the measurements with a lot of precision, you need to use a full physics-based model. And the more physics it has, the better. But if you want to go the other direction from measurements to system parameters, usually the more physics your model has, the more difficult it is to estimate the parameters. So people use reduced models or surrogate models, and there are many examples. For example, people use a TEC approximation instead of solving Maxwell's equations, right? People use mode theory instead of solving Maxwell's equations in the D region, and so on. So these are models that capture most of the dynamics that we are interested in and allow us to understand the data easier. The first exploration that I'm going to talk about is related to the reduced model for acoustic wave propagations. So what you can see here are the fluid equations that after some approximations, you can transform into a system of ODEs. And this system of ODEs can follow the rays that are together would build the phase of the acoustic wave propagating. And this is an example of what the rays can look like. They can start here, and then they can refract depending on the structure of the temperature of the background. And here I'm using a library called InfraGA. And when you have these acoustic rays propagating, all you need to identify are the background conditions, like, for example, the wind or the temperature, the pressure, or the mass density. And one interesting exercise that we can do is we can say, okay, this is the basic structure of the winds and temperature and so on. Let's perturb it a little bit with a control curve, and let's see how much we can recover that, okay? And that's the kind of experiment that I'm doing. Like, for example, let's say that there's an acoustic source that goes to space and then refracts back, and an acoustic sensor detects it in the ground. And there's a balloon with acoustic sensor also that detects the signal in the air. There's a limited number of temperature profiles and density profiles and so on that are going to reproduce these exact same measurements. And here what I'm showing is how I can, using these two measurements, I can recover the structure of the medium from across which these acoustic waves are moving through. It's very similar to an ionosonde. Another reduced model that I've been exploring, and I think it's could be useful, is related to acoustic pulses. In this, they also call these N waves. So, but not detecting the N waves like in situ, or measuring the neutrals. But I was wondering how the N waves how these acoustic pulses can manifest in slant TEC measurements. So in order to calculate the slant TEC measurements, you have to first define the electron density and integrate it, right? So this is the electron density. We assume that there's a background and a perturbation. So we are going to focus on the line of sight integral across the perturbation. And now the question is, what kind of perturbation in the plasma would an acoustic pulse produce? But we don't want to put all of the physics. We just want to put some of the physics that we think is dominant. And there's literature on this, on approximations of the momentum equation that captures, for example, the impact of the neutral modulation in the plasma velocity. And this is the perturbation in the plasma velocity. And if you integrate the continuity equation across some path, then you basically have a differential equation for the TEC, which would be tau here. So here, what this is saying to us is that all we need to do is to figure out the divergence of this perturbation of the velocity, and then that's it. But this perturbation of the velocity depends on the neutral velocity u. So we need a model for u. And the model that I'm using is this N-wave model that have been reported in several, in a lot of the literature. And if you plug this model into these equations, you're going to get this electron density perturbation. And if you integrate it, then you will have this equation, closed form equation for an electron, total electron content shape in terms of things like magnetization, the angle of the angle of propagation of the acoustic pulse, the line of sight of the TEC integration, the inclination of the magnetic field. And you can see how for different magnetizations, different angles, the acoustic pulse is going to not couple the plasma more or less efficiently, but be seen in the TEC more or less efficiently. So there are like two things that the acoustic pulse has to do. First, it has to couple with the plasma, and then it has to be seen by the TEC. And these two steps depend on these parameters, apparently. And these parameters seem to be able to explain some reports of asymmetry of these acoustic pulses with respect to the magnetic field, for example. There's also some ambiguity. So several magnetizations and angles of propagation with respect to the magnetic field, different configurations of these two can give you the same TEC pulse. And you can do, by the way, this black line is the N wave, the acoustic perturbation, and this other one is the perturbation calculated for the TEC that we would see if we detrend the TEC, right? And the different amplitudes correspond to different parameters that I use there, different coupling parameters, but also different measurement parameters. And you can do all sorts of things. For example, you can imagine that there's an explosion in the red star here, and there's a receiver here, and you assume that the direction of the waves is like a straight line, and you assume a lot of things, and you can calculate how well, what's the peak-to-peak amplitude of these TEC perturbations. And by the way, this is an illustration of how the different angles are involved in this measurement. But you can do a little bit better than that. You can actually use libraries like InfraGAD to trace the rays that acoustic waves would follow, and which would be these lines here. And then these arrows would correspond to the magnetic field, and this line here would correspond to the line of sight integration. And the different colors correspond to how large is going to be the amplitude detected by the TEC. And these are some examples of the time it takes to each ray to propagate, and the amplitude ratio, and so on. But this trick can be applied to a lot of different phenomena. So for example, if we use Hooke's model for gravity waves, that looks something like this. Hooke says, okay, the perturbation in the electron density is the real part of this function here, and this function depends on different things that are related to the dispersion relation of gravity waves. But once you have the perturbation, then you just integrate through it. And it turns out that you can actually build closed form expressions for the TC perturbations of monochromatic gravity wave. And it's going to look like this. This is a complex part, but you take the real part. And this is very good because if you have a closed form solution, you can derive it very easily. And if you can derive it, you can put it on a nonlinear optimizer. And a couple of parameters, well, quantities that you can get from here are these two. This is the apparent frequency, and this amplitude here. And what this is the distortion that a gravity wave, that a TEC will have at looking at the gravity wave with respect to the period. And A is a distortion for the amplitude. And of course, that makes sense because if you are watching a gravity wave moving in this direction, and for some amazing coincidence, the satellite is always on the crest of the gravity wave, you're not going to detect any perturbation. If the satellite is going in this direction and the gravity wave in this direction, you're going to underestimate the periodicity, and so on. So the direction of the line of sight and the direction of the gravity waves, and also the properties of the gravity waves can produce different distortions. And this is some example of that. So here I'm just plotting a gravity wave, very simple one, and this is a snapshot of a line of sight. And here I'm imagining that I'm measuring the electron density perturbations as the perturbations travel. And these perturbations are going to correspond to this line here. Oh, sorry, the red one. And here I'm showing two cases. One case where this term here is such that even though the periodicity of the gravity wave is this, you measure this other weird curve. And this other case, in which even though the amplitude of the gravity wave is like this, and you would measure that if you are in situ, you actually measure this change because of the geometry of the measurement. And I think that this could be helpful to characterize perturbations that are coherent enough that can be represented with this parametrization. So in summary, ray tracing, I think, is very promising. You can do inverse problems of ray tracing with acoustic and also gravity waves. A lot of people in other communities work with this. And there seems to be reasonably good closed form TEC perturbations. that can be that in terms or that depend on neutral modulations. I didn't show the clause, but if you compare these approximations with actual numerical integration, they are very, very similar. It's a very good approximation. Yeah, that's it. Thank you.
Thank you. We have time for a couple of questions. So, Pavel.
Yeah, that's just awesome. I just wonder, so you studied the kind of monochromatic gravity wave propagating, but in reality we have a packet of gravity wave of very broad spectrum, right? So you will have the phases tilted, well, differently, right? Different periods, different horizontal and vertical wavelengths. So is it still produce comparable results to what you are doing? That's actually amazing if they are comparable.
Yeah, so I would say that there is a subset of cases where the signatures are coherent enough that this is very directly applicable. But in the cases that you're mentioning, I think that's a very interesting problem. And if you take all of the jargon, it's a problem that I think can be attacked with something called like L1 or L0 regularization. So it basically what it does is it tries to look for the solution that uses the least number of components. So if I say, for example, this perturbation is a superposition of this number of modes, right?
Yeah.
Let's try to find the field, the perturbed field that is composed by the least number of modes. So this is a very interesting, fun mathematical problem. There's a lot of libraries. I wanted to include something like that here, but I didn't have the time. But yeah.
Okay, yeah, great. And for infraguide, so this is a linear retracer. So what are the sources of acoustic waves we may consider for well, using this approach? On the ground level, that would propagate in fairly linear regime. We studied acoustic even, let's say, with smallest detectable earthquakes, for example, and they still evolve to shocks, and that's why we all the time run this like computationally expensive numerical models to address the evolution to shocks and waves.
Yeah, I don't know a lot of the limits of applicability of the ray tracing approximation for acoustic waves. My understanding is that this is a standard tool even for events where you get some nonlinear behavior at some point, but eventually you see that the whole trajectory can be well described by acoustic speeds, and on the majority. So if my understanding is that if there is a shock, this is going to evolve non-linearly until some point where you can approximate that the perturbations are linear enough so this model can be a good approximation.
Okay, yeah, thanks so much.
Thank you.
Yeah.
Thank you.
Thank you.
So the next talk will be by Guiping Liu about concentric waves in geos.
Yeah, seems like my talk already be covered by many different talks. So I'm just giving a summary and should be short. So I will talk about the mesoscale concentric wave pattern generated by convection. So we're using a GEOS FP. You already heard about GEOS MLT. So GEOS FP is basically using the bottom of the GEOS MLT. It's only the lower atmosphere part. And GEOS FP is a GEOS plus data simulation. So it's an analysis product. So FP is forward processing. So this is majorly for doing numerical weather forecast. So we're using the GEOS FP analysis product at a quarter degree resolution, the high resolution version. And we're looking at the case study of GEOS FP during a Category 5 hurricane, Patricia, in 2015. So we just published this paper in JGR in May. So, so this is borrowed from John's paper. So now many studies have shown the different layers of the atmosphere, from the troposphere up to the upper atmosphere, are strongly connected. So like the low atmosphere forcing from different wave sources, they can largely affect the variability of the upper atmosphere. For the global scale waves, tides, some of them can directly propagate into the E-region ionosphere and then through the wind-driven dynamo affect the F-region ionosphere, driving the longitudinal global structures in the F-region, like in plasma density, things like that. And then planetary waves, either through the direct propagation or interaction with tides, they can extend the impact into the upper atmosphere, producing the multi-day variations in the ionosphere. Smaller scale gravity waves, they can seed ionosphere equatorial plasma bubbles. And we know TADs, they can drive TIDs. But for mesoscale gravity waves, they can also affect the ionosphere through different ways. They can drive the generation of medium scale TIDs, MS-TIDs. They can also modulate the F-region ionosphere plasma motions and density distribution and affecting the ion-neutral coupling. Also, mesoscale gravity waves, MGWs, they can generate acoustic gravity waves, and these are important for radio occultation and causing scintillation in communication. So on the right, there's a paper by a group back many years ago, shows the ionosphere modulations with a horizontal wavelengths at several hundred kilometers and periodicity between half an hour to 1 hour. So maybe these indicate the MGW signature in the ionosphere. And I will skip this. And also this. So basically, the previous two slides, just some basic information about GEOS FP. It's an analysis product again, and we're using the quarter degree resolution. So for our study, we use a 3-hourly global output from GEOS FP. So this includes 72 vertical levels from the surface up to about 75 kilometers. And the vertical resolution is 2 kilometers in the upper part of the model output. But remember, so the model top above 70 kilometers is a very thick spongy layer. So any results above this level are not reliable. So we just use the results between 20 to 60 kilometers. And because of the resolution, so only waves with horizontal wavelengths greater than 100 kilometers in horizontal wavelengths and vertical wavelengths larger than 6 kilometers can be resolved. And keep in mind, because of the strong damping near the model top, so the wave amplitude are largely reduced. So to derive the mesoscale wave signatures from the model output, we follow several steps. First, at each vertical level and each latitude and longitude grid, we first remove the tides, so including 24-hour, 12-hour, and 8-hour oscillations. And then these global residuals are fed to a spheric harmonic with zonal wave numbers from 0 to 4 to isolate the large-scale rotational background fields. And finally, we do a 9-hour rounding average to remove any fluctuations at shorter time scales. So these final results showing the perturbations in the GEOS FP output. So here, there's a movie showing at each 3-hour time step what the perturbation looks like. So apparently, we see several hotspots, like in the Andes. And they form a concentric wave pattern. But the interest part is over the North American region. Yeah. So this time window, it's the Hurricane Patricia in 2015. So it occurred over the North American region. So we'll look at that in more detail. So here is a snapshot of over the North American region of these perturbations from GEOS FP on the top. So this is during the hurricane peak, and this at 40-kilometer height. So yeah, this concentric wave signature is clear, and we highlight the region of this concentric wave pattern over North America. And the bottom is from observation from EOS. Yeah. So EOS is a infrared radiance measurement, mostly between 30 to 40 kilometers in the stratosphere. But overall, the concentric wave patterns captured by GEOS FP was showing in the observation, even though there are some differences. So here, the box highlight this concentric wave pattern where they are located. But the Hurricane Patricia, it's outside this box. So these concentric waves are not generated by the hurricane. But when we look at the daily weather map from NOAA, so this box actually coincident with very strong thunderstorm activity and the rain precipitation. So this indicate, even though there's a concentric wave, the mesoscale, these wave structures are not directly generated by the hurricane, but it may be associated with the hurricane in the outer bands of this hurricane trajectory. So now we look at these mesoscale wave perturbations we got from the GEOS FP. So the middle column showing during the hurricane event, and the left and the right column showing before and after. And these are different vertical levels from 20, 30 to 60 kilometers. So first, the wave amplitude apparently increased with the altitude. So this indicating these waves are generated from the troposphere, and they propagate upward. And this concentric wave pattern is less clear before and after. So showing again, they should be associated with the hurricane. And then we look at the wave properties. So this just showing some wavelet spectrum. But so this showing the zonal wavelengths of these mesoscale waves are several hundred kilometers in horizontal, in zonal and meridional wavelengths. And in vertical wavelengths, the wavelength peaks around 15 kilometers. And look at the skewness of the power spectrum. It's skewed at higher altitudes, so indicating longer wavelengths can only propagate into higher altitudes. So now we look at the time mean momentum flux to quantify this mesoscale wave impact into the background zonal flow. So we're using the time mean momentum flux equation derived by Chambers back many years ago. So here we plot the vertical component, in the contour plot. So look at the contour plot in the color. So we see this concentric wave pattern again in the Z component of the timing momentum flux. So these are consistent again with the vertical propagation of these wave structures. And then on the right side, showing the time evolution of this momentum flux. Again, the momentum flux are largely enhanced during the hurricane event. Okay, so in summary, this study shows that the GEOS-FP high-resolution analysis product is able to resolve the mesoscale gravity wave structures. And, but we still need to build a whole atmosphere model and include many observations in order to understand how these waves are generated, propagate, and their impact on the upper atmosphere and the ionosphere. So finally, advertisement for AGU. So we're organizing a session including observations, modeling, and new techniques, new technologies. Thank you.
Thank you, Gui Ping. We have time for a couple of questions. Jim Hecht.
Yeah, very interesting talk. I think one of the problems, though, is the models and even the data to date are missing the small scale portion of the spectrum. So we had an instrument piano on the space station, and we observed Hurricane Ian when it was just about Cat 5. And so the waves we saw, which were semi-concentric, were about 35 to 40 kilometer horizontal wavelengths, which are consistent with what you see in air glow imagery. So I think there's maybe still a missing portion that's not being accounted for in the observations and the modeling. And, and even in this TID stuff, I mean, the resolution of that, I don't know what the small scale horizontal structures they can observe, but I suspect they're not 30 to 35 kilometer.
You're right.
Okay, then thank you, Gui Ping. So we have two talks left, both related to stratospheric polar vortices, and the first one will be by Sunil Kumar. So Sunil is about to finish up his Jack Eddy Fellowship, and he was actually working with me.
So in this talk, I'm going to show how the northern and southern hemispheric polar vortices on the upper atmosphere differ to each other. So there are numerous studies about the impact of the northern hemispheric polar vortices on the upper atmosphere, but the knowledge about the impact of southern hemispheric polar vortices is relatively less known. So I'm not going to discuss what is the polar vortex, but we all know. But polar vortex stability affect the whole atmospheric dynamics, and it produce substantial changes in the upper atmosphere by filtering upward propagating waves, especially solar and lunar semidiurnal tides. So in this talk, I am going to show the SW2 solar semidiurnal tidal variability with respect to the polar vortices strength. So for this study, I have used the ST Wacom data for around 43 years. And here I am showing the SW2 as a function of latitude and day of the year for 2 boreal winter and for 2 austral springs. And on the top of this figure, the white lines show the NAME index and SAME index. NAME is Northern Annular Mode, and it has been used as a proxy for the northern hemispheric polar vortex strength, and so SAME for the southern hemispheric polar vortex, and when their values are negative, it means polar vortex is weak, and vice versa. So we can see that around SSW time, when polar vortex is weak, we can see the SW2 enhancement. And for boreal winter, it is very well known. And this is the statistical result. So we can see that, yeah, around 15% SW2 variability is dependent on the name and northern hemispheric polar vortex strength. But similarly, during Australia spring, when the southern hemispheric polar vortex is weak, that time we can also see enhancement in the SW2 amplitude, similar to the northern hemispheric polar vortices strength, and the statistical result also show similar kind of SW2 variations. But if you look the slope values, then the slope between SW2 and NAME is almost twice than the slope between SW2 and SAME. It means SW2 is less sensitive to the SAME than NAME. So further we investigated that how the SW2 latitudinal variability varies with the strength of the polar vortex. So for that we have used the tidal half modes. Those we present by the S and N. Here S is the zonal wave number and N is your meridional mode number. And for SW2 tide, first four half mode look like this. So here HM1, first half mode 2, it is 2-2, and HM3, these are symmetric to the equator, and half mode second and half mode 4, those are antisymmetric to the equator, remember that. So the statistical results of each half mode with the name in the top, in the first row, in top row, and with the same in the bottom row look like this. So we can see that all half modes show significant variabilities with the name values, but the variability is leading by the half mode second, like antisymmetric half modes. But when we see the amplitude anomalies of each half mode with same, and we can see that only half mode 3 show a significant variabilities. So it is only for a particular altitude, but their variability can change at different altitudes. So using superpose analysis for the weak and strong polar vortices, here I am showing the each half mode's variability when the polar vortex is weak and when polar vortex is strong for the northern hemisphere and for the southern hemisphere. So we can see this second half mode show largest variability in the upper mesosphere and lower thermosphere, and it is followed by half mode 4. But as we see, they are showing reduction at lower altitudes. But when we see the half mode first, it is almost constant throughout the altitudes, and half mode 3, it shows largest enhancement at lower altitude, but the enhancement decreases at higher altitude. And the variability is totally opposite when the polar vortex is strong, and in the case of the southern hemispheric polar vortices, only half mode 3 shows significant variability, as we can see here by blue line. So this is consistent with the statistical results as well. So in further investigation, like what could be the reason of these different kind of variability of the SW2 tide? So there can be two reasons, like if there is any change in the background wind that can filter the SW2 tide differently, and if there is change in the source, like we all know that SW2 tide is generated by heating of the stratospheric ozone. So if there is any change in the ozone distribution, that can also change the SW2 tide. So first of all, for the northern hemispheric polar vortices, we analyzed the change in the solar heating. So here I am showing the SW2 component of solar heating at 2 SPA, where your ozone heating peaks with latitude and day of the years, and this black dashed line show the name values. So we can see that during SSW period when polar vortex is weak, that time we can see an enhancement. And then we further, when we decompose it into different tides, those are shown in different half modes, those are shown here along with their climatology shown by the dashed line. So we can see that there is small change in the first half mode, but other half mode doesn't show any significant variability for this particular SSW event of 2008 and 9. And for another event, it also show around 10% enhancement, and that is associated with the first half mode, but other half mode doesn't show anything. So we know that all half mode has showed significant variability with the name, but your change in source show a significant variability in only first half mode first. So further, like, is there any like the background wind that can affect the half mode's variability? So for that, like, it is well known that if the winds are antisymmetric to the equator, they will support the antisymmetric half modes and vice versa. So then we analyzed the U and absolute difference of zonal winds over mid latitudes where half modes peak from northern and southern hemispheric, and those are shown here in the first column for 3 different events. So if UN these values are larger, it means winds are very antisymmetric, and if their values are lower, then it means winds are less antisymmetric. So we can see that during SSW, the winds are becoming symmetric around this period for all the event, and concurrently we can see the enhancement of the symmetric half mode first and half mode third for all the events. But in the upper mesosphere and lower thermosphere, winds are becoming a bit antisymmetric. So at that time, we can see the enhancement at higher altitude of the antisymmetric half mode that we can see here, the enhancement of HM2 and HM4 for all the event. So that is consistent with our superpoke analysis, like the antisymmetric half mode decreases at lower altitude and increases at higher altitude, but the symmetric half modes are showing consistent enhancement throughout the altitude. And for the southern hemispheric polar vortices, when we investigate the or we analyze the change in the solar heating at 2 HPA, then we found nothing. Like, there is no significant change in the ozone distribution corresponding to the southern hemispheric weak polar vortex. Like, around when that same polar vortex is weak around these 270 days, and there is nothing. There is no significant variability in any of the half modes. But further, then similarly we analyzed the change in the background wind, and we found that during southern hemispheric polar vortices or southern hemispheric SSW, the winds are quite symmetric throughout the altitude. And when the when the winds are symmetric, that give rise to the enhancement of the symmetric half mode that we can see here for HM1 and HM3. But at the same time, we can see a decrease of the antisymmetric half mode HM2 and HM4. So based on these results, it is clear that northern and southern hemispheric polar vortices can produce different kind of changes in the upper atmosphere. So for the ionosphere, first we analyzed the model results where we used the SD Wakamax wind field for the nudging into the Tajicium. Those are shown here for the 300 kilometers. So it show SW2 relative variation as a function of latitude and day of the year. And you can see during SSW period, there is enhancement in the SW2 in electron density, but it is large in the northern hemisphere than the southern hemisphere. And it matches very well with the cosmic 2 observation as well. So at that time, we can see in the neutral wind, the there is enhancement of the symmetric half mode and antisymmetric half mode. So because of the interference of the symmetric and antisymmetric half mode, they lead to the this antisymmetric variation in the SW2 electron density. And for the southern hemispheric event, we can see the SW2 enhancement is quite symmetric to the equator. And it is because of the enhancement of the symmetric half mode correspond to the southern hemispheric polar vortices. Yeah, also there is small enhancement in the half mode 4, like antisymmetric half mode, but I am not showing here due to the time constraint, but the contribution in the ionospheric electron density by HM4 is very negligible as we compared it with the other half modes. So this is conclusion. So for more detail, please go through this paper, and the home tech message is like the northern and southern hemispheric polar vortices can affect the upper atmosphere differently. Thank you. Thank you for your kind attention.
Thank you, Sunil. We have time for one quick question. Okay, thank you, Sunil. So sorry for running a little late. So the last talk will be given by Larisa Goncharenko, which I think is very befitting because Larisa is also a co-convener of this workshop, and we couldn't have done it without her. So Larisa has a short talk about ionospheric responses to the stratospheric polar vortex.
Excellent, thank you. I will try to be very brief, and this goes along with previous speaker. And in this work, we're actually trying to understand what happens during strong polar vortex conditions, as physics of what happens during weaker polar vortex conditions is known quite a bit better. Very briefly, a lot of our understanding of what happens during strong polar vortex condition comes from simulations. There were several papers on this within last several years. What they predict to see is decrease in SW amplitude in the MLT region, and decrease associated with the decrease in zonal mean electron density at low latitude. There are several simulations by WECAM-X, but UA-ICON within last literally a couple of years, and they're pretty consistent. And as you see in this type of figures, one of them we just saw before, all simulations are pretty consistent that during strong polar vortex, strong NEM conditions, amplitude of SW2 is expected to decrease. What do we see in data? There is not much is known in data, but Dipali had a paper recently when she looked at both simulations and observations from COSMIC, and saw similar variation, that decrease in cosmic electron density during strong polar vortex conditions. So what we do in this work, we want to actually understand what is seen in observations. We focus on peak electron density in ionization data. We look at NEM index to identify strong polar vortex conditions, and we, in particular, we look at NEMs higher than 1.8, identify several events, and to understand what happens in the ionosphere and attribute it to polar vortex, we use local models, ionization models of peak electron density. And I specifically want to show here, for example, what we see, what we can expect from the model. Typical mean absolute percentage error during wintertime conditions. These figures are a function of day of year and local time. During daytime conditions, model are so accurate, we expect median average percentage error of the order of 15% or even less, 15 to 17%. So things that are anomalies that are above that, we are very interested in those, trying to investigate them. And right set of figures just shows comparison with IRI. So this is the reason why we use local empirical models to understand this, characterize data and data. Just highlights of some results. When we look at strong polar vortex conditions in January 2009, and we look specifically in the mid-latitude ionosphere, we see really quite unexpected variation when for several days in a row we see strong enhancement in morning to early afternoon for multiple days. Enhancement is very consistent in behavior in local time and reaches up to 60% variation compared to the background state. Anomalies of the order of 30 to 60%. Another important point about this is really significant longitudinal asymmetry and longitudinal variation, because we do not see similar behavior in the American sector. During morning hours, we see perturbations of the order of what expected day-to-day variability, and we see weaker positive anomaly in the late afternoon hours. When we look at all available data during this particular event and looking in the noontime sector, what is very interesting to me, we have a patch of positive disturbances over European sector. Each red dot is a different station. They are completely different stations run by different countries, and for different years, they have different like for different number of years, and each one of them has very specific empirical models. But they're very consistently, they show positive anomaly over Europe. And as you can see, we do not see similar picture over continental United States or, for example, over Asia. But to make it even more puzzling, we actually see patch of negative suppression in electron density, quite significant, of up to around 15 to 20% of Australia. So one of the points about this, we continue investigating. Ongoing work, we are running whole-day incoherent scatter radar campaigns during strong polar vortex conditions. We had a couple of campaigns in the past, and we'll be planning to run again. And this is example what we see in mid-latitude locations with Milestone Hill incoherent scatter radar. Weak vortex, pretty much smooth electron density and pretty high. Under strong vortex conditions, much lower background electron density, which would be consistent with Nick-Pedotel simulations, but this is mid-latitude again, but stronger TIDs, in particular larger scale TIDs. So very quick summary, we focus on observations. We see unexpected signatures, in particular at middle latitudes. We see positive anomalies up to 30 to 60% in one geographic sector, but negative anomalies up to 10 to 20% in another geographic sector. We're looking at temporal development of this, looking at what happens in the thermosphere, thermospheric composition. There is no consistent picture at lower latitudes. So we do not see what is predicted to see just from SW2 perturbations or decrease. So what we interpret that this results suggest that there are more complex mechanisms in play than just SW2 variation, and I find it really quite interesting. Looking forward to more results. Thank you.
Thank you, Larissa. Everyone is tired, but I have a question. So what, I understand that you're still investigating what kind of causes these rather puzzling high-low patches in NMF2, what you showed, but what's your educated guess?
My educated guess is non-migrating tides and probably changes in phases of tides and superposition of different tides that produces these like very regional patterns of variations.
It would be actually pretty cool to look into what Manbarat showed basically using the new HWM version and plugging that into SAMI 3 and see what gets out of that.
Absolutely. And when I saw what he showed, that just inclusion of non-migrating tides can lead to up to 30% changes in electron density in TAC, that's huge. So I'm looking forward to discuss more and to see more results on this.
Okay. Thank you, Larissa. So this concludes this 3-year Grand Challenge workshop. So yesterday, Chen Lu asked me, what did you guys actually learn the past 3 years? Hopefully you got kind of an impression about that today. I think we, as a community, we really made good progress, very good progress in terms of understanding what really the lower atmosphere is doing to the upper atmosphere and what's really the physics that plays a role there. So I would argue probably the two really important outcomes are, first of all, we have seen what we can do when we actually work together as a team, because also part of this Grand Challenge workshop came out of a Living with the Star focused science topic that was a kind of seed for the whole thing, and then doing that here at CEDAR to involve the broader community here in aeronomy. And secondly, I would say all these the new insight into physical mechanisms will, it's my prediction, turn out to be quite useful for the new Grand Challenge workshop we heard about yesterday from Jaga Richter and co-workers, and which is more focused on predictability of the whole system. And I would argue we did part of our job, what's coming in terms of physics and mechanisms from the lower atmosphere. Now we have to see what's going on and what does this mean really in terms of prediction in the future. So that's it, and thank you very much for staying around, and enjoy the posters. Thank you.